All right, my strange addiction is wanting to do indefinite integrals immediately after lunch. Wow, I gotta get at them. All right, here we go. E, we were exploring letting the square root of 2x be u. And we got down to this right here, and we want to see how that helped, right? So we're in the process of evaluating how it helped, and it hasn't. So here's the idea. When you do u substitution and you change the variables and you get it down to something like this, you need to kind of reset your mental flow chart in terms of what to do, because every method that we've learned could be viable once again, including a possible u substitution, which then we would have to use a different variable. So is there anything that we've talked about strategy-wise that would work here? There's nothing to expand. I can't split up the denominator. What if I call it u plus 1? Commutative property of addition. Good strategy. Yeah, but then I can't distribute anything in, you know? So if there's, I'm just kind of thinking if there might have been something up here. Oh, yeah, long division. Yeah, it works when the degree of the numerator is greater than or equal to the degree of the denominator. So, yes, we might have to do one of the methods that we've already learned as a second method in a particular problem. So here we go. We're going to have u divided by u plus 1. How many times does u go into u? U goes into yourself one time. You left with u plus 1. You subtract, you get minus 1. Does u go into negative 1? No, u doesn't. So this becomes then the integral of the quotient 1 plus the remainder, which is really minus 1, over u plus 1 du. And now we've got it, right? The first term becomes what with respect to u? U, good, minus the second term has an inside function of u plus 1 in the denominator to the first power. Its derivative with respect to u is 1. We're not off by anything. So what's the rule of integration? When it's in the denominator to the first power? ln of the absolute value of u plus 1 plus c. And of course, because it's u substitution, what we do at the very last step, if we haven't done it already, is replace u back to what u is. And what is u? U is the square root of 2x. So the final answer becomes the square root of 2x minus the natural log of the absolute value of the square root of 2x plus 1 plus c. And there you go. No. Good call. You, in fact, the square root of 2x plus 1 is entirely positive, so you wouldn't lose anything by dropping them there. Yeah. So there you go. A combination of methods. That's what makes these so darn fun. Multiple strategies per problem. All right, we're going to come back to D if we have time. I want to make sure I get through this. We've alluded or worked a couple of problems this year where we've had symmetry, and we've used symmetry to help us with our integrals. And when we get to polar area, again, we're going to be using symmetry practically on every single problem that we set up. So this gives us just a nice little table that summarizes integration properties for even and odd functions. And of course, when we refer to an even function, we're talking about a function that has what? Y-axis symmetry, right? And an odd function has origin or rotational symmetry. So if you're integrating an even function from negative a to a, that is on a symmetrical interval, which hopefully when you read a definite integral, that's the first thing you notice, right? The integral from like negative 5 to 5, negative 1,000 to 1,000, something that's symmetric. If it's an even function, you have the option of integrating on half the interval from 0 to a and then doubling the result, okay? Now, why would you want to do that? Well, if you're evaluating it by hand, let's say you're going from negative 10 to 10. When you use the fundamental theorem to evaluate, you'll plug in the top, you'll get 10. But when you plug in the bottom, you're going to have to plug in a negative 10. And plugging in a negative number, yucky, yucky, gross, gross. So you have the option of going from 0 to a and plugging in a 0, which is a lot nicer number to plug in. And then you can double it. It's even better, as we've seen, if your function ends up having origin symmetry and you're integrating on a symmetrical interval, because then the net accumulation is always 0. Very easy, okay? And here's a graphical interpretation of why. All right, so let's look at example 25 and see if we can put those qualities into good use here. All right, 25a. We have the integral from -3 to 3. Ding, 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 ding. Symmetrical interval, symmetrical interval. So that should put you on high alert for some type of symmetry that you could use to make the calculations easier on yourself. Now, if you were to take the whole function by itself in one big bite, you'd be like, I have no idea what that graph looks like. I don't know if it has origin symmetry or it has y-axis symmetry. You don't have to take it in one big bite. Remember, the property of integrals allow you to take the integral of each one of these terms separately. So you can analyze each term effectively for its own symmetry and then break it up accordingly if you need to. So let's do that. Sine of x, we know, is what type of symmetry, even, odd, or neither. It's an odd function. X cubed is an odd function. This one here, let's review the test. There's an algebraic test for symmetry. The test is you replace x with -x. If you get the exact same thing you started with, then your function is even. If you get the opposite of what you started with, then your function is odd. And if it's in between, it's neither. Yeah. We also had this. An odd acts like a negative number. So an odd over an odd is an even. An odd over an even is an odd. An even over an odd is an odd. And of course, an even over an even is an even. Okay? They act like negative numbers. So you could do this by that. X squared plus 1 in the denominator is what? Even or odd? Even. And then x itself is what? Odd. So an odd over an even is odd. So this is an odd function together. So all three terms are odd. We're on a symmetrical interval. Guess what the net accumulation is of the whole thing? 0. And you don't have to do really any calculus at all. Now, could you do the calculus and get the same answer? I trust that you can, right? What would the antiderivative of sine be? Negative cosine? Negative cosine. Negative cosine. Yep. And then x cubed would become 1/4 x to the 4th. And then this one, the third term, would become, it wouldn't be arctangent. The derivative of x squared plus 1 is 2x. You're off by a 2. So you'd have a 1/2 natural log of the absolute value, unneeded, of x squared plus 1. And then evaluate it from -3 to 3. Oh my gosh, plug it all in. Combine like terms and get what at the end? 0. You can verify at home. So when you're integrating on a symmetrical interval, look for symmetry. It'll be a real time saver. Letter B, the integral from -pi to pi. Symmetry. Term by term. Is one even or odd or neither? It's a horizontal line, y equals 1. Every constant is going to be an even function, yeah. X squared, even. Cosine, as it lets me call them, cosine, even. So is it 0? They're all even. No, that only works for odd. So we are going to have to find the antiderivative, but we have the option of integrating from 0 to pi and doubling the result. I'm going to show it in a separate step. Now, you could also double the result from -pi to 0, couldn't you? Yeah, you could. But why would you want to do that? The whole purpose is to get rid of the freaking negative number, bless you, bless you. I mean, if you like a challenge, feel free. Not me, I'm going to be smart. Okay, so twice beefy bracket, we get x plus 1/3 x cubed plus, oh my gosh, I get these confused all the time, the antiderivative of cosine. Negative sign or positive sign? Positive sign, let me check. Got it. Okay, good. From 0 to pi. All right, 2 goes along for the ride. Now I got to plug in the top. I get pi plus pi cubed thirds plus sine of pi. Sine of pi, sine of pi. That is 0. Minus. Now look, instead of having to plug in a negative pi, yucky, yucky, gross, gross, I get to plug in a what? A 0. 0 plus sine of 0 is 0. Yeah. Now, you may not always get 0 when you plug in a 0, but it will be easier than plugging in a negative pi. And so your final answer is 2 quantity pi plus pi cubed thirds. Ta-da! Symmetry, much like parentheses, could be your best friend in a math class. And then letter C, the integral from -1 to 1. Symmetry. Now notice we have a 5th degree polynomial. And remember, there's an easy test for polynomial symmetry, right? If you replace x with -x and none of the signs change, it's even. And if all the signs change, it's odd. And if some change and some don't, it's neither. So let's go ahead and see if this is even, odd, or neither. Will the first sign change or stay the same? It's an odd exponent, so it'll change, right? And you plug in a -x, it becomes negative. So that one changes. X to the 4th stays the same. Crap. So the whole function is neither. This function has no symmetry if you graph the whole thing. So I guess we just have to evaluate it by the good old power rule. Or do we have to throw the baby out with the bathwater? Can we salvage the bathwater? I mean the baby? Did you see the NFL had all those commercials last night about procreation after the football game? Wow. No, we don't. Because we can split up terms, giving them their own integral, we can actually collect all of the odd terms together, like 5x to the 5th plus 11x cubed minus 15x. Those are all the terms that are odd. Give them their own integral and their own dx. And then plus, notice since the other ones are even, we have the option of going twice from 0 to 1 of the other terms, x to the 4th plus x squared plus 1. So because it was a symmetrical interval. Now, that's going to be helpful because what happens to the integral of the first 3 terms? It becomes 0 without any work. And so what we really end up doing is we're having to integrate half the terms on half the interval and then double the result, which makes for pretty easy work. So 1/5 x to the 5th plus a third x thirds. Puppy monkey baby. Puppy monkey baby. From 0 to 1. That was a creepy one for sure. I didn't know where that one was going. That makes those Skittle commercials seem downright normal. All right, so you get 1/5 plus 1/3 plus 1. There's plugging in the top. Minus. Now, instead of having to plug in a -1, bother, we get to plug in a 0. 0 plus 0 plus 0. 0. I hope you're convinced that symmetry is worth it. And I'm going to leave it right there. You can find the answer. So we can look to use symmetry when we are integrating on what type of interval? When we're integrating on a symmetric, yeah, it doesn't really, it's not as important to look for symmetry if you're not integrating on a symmetric interval. I guess you could break it up using the additive interval property. Like if I was going from -3 to 5, I wrote that a little different, didn't I? There we go. If I'm going from -3 to 5, and you realize your function is an let's say you realize that f of x is odd, and it's not a symmetrical interval, you could use the interval property, right? You can go from -3 to 3. You might, right? Because then you can go from 3 to 5. Right. So then that would become 0, but you'd still have pretty much just as much work to do, right? It's not going to be a saver in terms of work. It's going to make your interval smaller, but you're still going to have to find the antiderivative. You're going to have to plug in a 5. You're going to have to plug in a 3. So, yeah. Anyway, symmetrical interval is really nice. All right. I guess then we have time. Do we have time? Let's retreat to letter D. All right. You walk up to the problem. You're like, what's up, problem? Hey, problem. Did you know that there's a spike in births 9 months after the winning Super Bowl team city wins? Did you know that? Yeah. They're called Super Bowl babies. because their parents celebrated after the game. Hey, did you know Peyton Manning's drinking Budweiser? Lots of it. What kind of weird Super Bowl was that? Advocating sex and binge drinking? My gosh. Ugh. I walked out of the room for the halftime show. All right. What? How can we proceed? What about me? Yeah. U sub. Okay, what would you call U? 1 minus x? Let's try it. If u is 1 minus x, then du is negative dx, and dx is negative du. So I would get 1 over, that would become the integral of the square root of, that would become u. And now I would need to solve that for x, so x would become 1 minus u. So then I can plug that in there, and I get the square root of 1 minus u. And then dx becomes negative du. That looks like the opposite of what we started with, literally, right? Which means we're no better off. But you know what? We haven't failed. Not like Carolina failed to win the Super Bowl last night. Although it was a good game. Too soon. We have successfully found one way that will not work. Just like the Seahawks successfully found at the end of the Super Bowl 2 years ago that they should not run beast mode on the last play of the game, or fake the beast mode. They should run beast mode, not try to pass. You successfully find one way. This is how we successfully don't win the Super Bowl. So next time we're not going to do that. We successfully found one way that will not work, so we're not going to do that again. So let's try a different substitution. What else could we do? It was good, worth to try, right? You get experience that way. Making u what? The square root of 1 minus x? Okay. Let's try that. So that would become the integral of, you were just waiting for me to make a Super Bowl joke. I could tell. It was hanging in the air. And I said like Latin. Oh, the oohs came, sorry. If I square both sides, here's a case where instead of taking the derivative, I'm going to square both sides and get 1 minus x. And then take the derivative differential form, we get 2u du equals negative 1 dx. And so dx would equal negative 2u du. Okay, so I can replace dx with all of that, negative 2u du. And now all I have left to do is replace that. Oh, let's see. Oh boy. So if I solve for x, I get x equals 1 minus u squared. And so if I plug that in here, I get the square root of 1 minus u squared. Does it? Hey, you see that? I see that. Holy moly smokers. And the negative 2 comes out front, and I'm left with 1 over the square root of 1 minus u squared, du. That is totally arc what? Arc sine. It's straight up arc sine. It's not even one of the forms that we memorized. That is the derivative arc sine of u. So we got negative 2 arc sine of u plus c. And we box it up and we walk away? No. What is u? What? Q is the square root of 1 minus x. Wrong problem. 1 minus x. Yeah. There you go. Plus c. So u substitution is a very good tool to use for explorational purposes as well. You can kind of sample with things because it does give your integral a very different look. And when it looks different, then you can kind of reset your mental flow chart and kind of go through all the little procedures again. You just got to remember to plug back in at the end. Awesome. All right, there was one on the worksheet where someone pointed out that I had it wrong on the key. So let's look at it. And it's a very easy error to make. So from the worksheet 4.4, I will look at example 14. Now, College Board will ask a question more than likely, like on a multiple choice question, where they're saying if the substitution u equals this is done on this integral, what's the result? It would be a similar question to this. Same idea. It says use u substitution to answer the following. A, if the integral of dx over 1 plus cosine of x equals tangent of x halves plus c, find the integral of 1 over 3 plus 3 cosine of x fourths. Exactly, right. Where c is a constant. Yeah, exactly. Well, what are we going to do exactly? Well, we're going to have to make this form fit this form here. Okay? That's what we're going to have to do. And it looks kind of similar. The first thing you might notice is that this is a 1, and the coefficient of cosine is a 1. And over here, they're both what? 3s. So one thing you could do immediately is factor out a 3 from the denominator, which is factoring out a 1/3 from the whole problem, and that makes it look a little bit closer to what we want. But we're still not quite there, because now I need this to be a plain old single variable with respect to that. And I have it being an x over 4. So guess what I can do? I can let u equal x over 4, which is 1/4 x. And here's what the replacement will start looking like. I'll have a 1/3, 1 over 1 plus cosine of u, right? But here's the key. I can't just put du there. I actually have to figure out what du is. So if u equals 1/4 of x, if you want to multiply both sides by 4 first before you take the derivative, then it's up to you. Now the derivative in differential form is 4 du equals dx. And so I can replace dx with a 4 du, and where can the 4 go? In the front. And now I have a du. So once you do the u substitution, again, for all practical purposes, that u can be any variable. It can be a PDP, an MDM, even an x dx. All right? So what is that going to equal? Well, it's a 4/3 times. Now here's the thing. It's whatever this variable is. X becomes tangent of x halves. So mine is a u, so it becomes tangent of u halves plus c. Whatever that variable is, it fits that form. Now, on the worksheet, I made the quick mistake of just calling it x halves, which is a very common thing to do, not to substitute back in at the end. So I do need to put it back in terms of x. So what was x temporarily? Or u was standing in place of 1/4 x. So what's half of a fourth? 1/8. So you can call it 1/8 x plus c, or you can call it x over 8 plus c, whatever you want. And that's the correct answer. And on the key, I believe I wrote it as 4/3 tangent of x halves, which is, that would make a great multiple choice answer choice. You get hasty at the end, and you kind of just let your hand finish up the job while your mind is thinking about puppy monkey baby. Yeah. Okay. You'll do something very similar on 14b, and on 15 you'll do something similar as well. But on 15, there's one slight difference here. It's a definite integral, so when you let u equal 5x, if you change your intervals of integration, which are x values to u values, it'll match the form from 0 to pi. So those are good problems right there. And that's it. We're done with this section. The worksheet's actually, I think, shorter than the notes. The notes is 11 pages long, and the worksheet's only 7 pages long. Now, there's one problem that has like a whole alphabet full of problems. I think number 12, like A through Z. But they're all quick pattern recognition ones. So you should be able to go pretty quickly. And that's the idea, to go rapidly. All right, so worksheets due tomorrow. Tomorrow we're going to look at 5.1 briefly. And then I'll let you know my decision about the test, like how many questions it's going to be, what the free response is going to look like, whether you can take it home with you or not. No, maybe. Not necessarily, no. No, maybe no. No. Friday. The only benefit to that is we get a whole nother day of instruction. And it helps Sean out, which is really what I'm after. It does help. Sean is looking out for everybody. Yeah. I'll let you know.